Hello viewers. So in this session we will continue to discuss on volumetric strain. In the volumetric strain, in the previous video we have discussed on uniaxial load, and the load is applied only in the length direction. In this session we will discuss on when the three mutually perpendicular forces are acting on each faces of a volume. In this figure we can see sigma x in either direction, in the length direction we have applied as a tensile force, and sigma z and sigma y. So that means three perpendicular faces. This is in a x direction, and this is in a y direction, and this is in a z direction. The load is applied which are tensile in nature. So now we all know that volumetric strain can be written as, that is, change in volume to original volume, right? That is change in volume to original volume, and we need to derive for this, that is original volume is nothing but L, B and T, and we all discussed this in the previous video. And change in volume. So when change in volume occurs, once the load applied are seen on the each faces, the dimensions will change, that is final volume minus original volume. Final volume minus original volume. So what is final volume now? The final volume is nothing but the change in length, that is L plus delta L, when the load is applied considered in the length direction. And with respect to this only I will discuss, when the load is applied on the length direction, this is L plus delta L, and with respect to thickness, this is T minus delta T, that is T minus delta T, and with respect to width, B is B minus delta B, right, when the load is applied in the length direction. At the same time, when the length is applied load is applied in the thickness, that is in a width direction, then the other two part will get minus, and at the same time it is similar to in the width direction, the other two part will get minus sign. So now as this part we have already discussed in the uniaxial load applied on the volume, so we comes out to be at that point we got delta L by L minus delta B by B. The similar derivation is to be followed to get this equation, that is change in volume, that is volumetric strain for delta L by L, delta B by B and delta T by T. So this equation we have already obtained from this part, substituting back here and multiplying the terms and substituting in this first equation, and we have obtained this strain, volumetric strain. So if you see the previous part, so this is what we have multiplied, and we have discussed this terms for multiplication, and we have substituted that in the change in volume, and we have obtained change in volume and original volume, substituted back, and we obtained this part, right. So now we will continue to discuss from this part for the this particular three mutually perpendicular forces. So now I will rewrite this strain, that is volumetric strain, that is what we have obtained, delta L by L minus delta B by B minus delta T by T. So now this, if you observe this delta L by L, it is nothing but strain, right, which is nothing but strain. So what we do write for strain, we all know this Young's model is equal to stress by strain, and for this what I can write, I can rewrite this equation for strain equal to stress by Young's modulus. So similar term I will substitute here to rewrite this delta L by L. That I can write stress in x direction for E. So E will be constant as it is a homogeneous material. Sigma x I have written because this is in a x direction. This is z, this is x, and this is y. So x direction representing length, and y direction representing thickness, and z direction representing width, if you refer this diagram, right? So now this can be written as sigma x by E for strain in x direction. Similar way, if I write for strain in z direction, what I can write? Sigma z by E. Similarly, strain in y direction I can write sigma y by E, right? So now strain in x direction if I write, so strain in x direction if I write for all the three mutually perpendicular forces, so 1 by E will be common, considering these terms with respect to delta L, delta B, and delta T. So, right. So now 1 by E will be common from all the equation, and which remain sigma x minus, so minus delta B by B, which we have discussed for Poisson's ratio. Poisson's ratio mu, that is linear to lateral to linear strain, lateral strain to linear strain. So that is lateral strain to linear strain. So in this part, so delta B by B when the x direction or in the length direction if we are considering, this will be minus mu times sigma, that is B in the z direction, B by E. So E however we have taken outside, again we have one more which is sigma y, mu times sigma y. Okay, so this is nothing but strain in x direction. So that means when the load considered in the length wise. So now if I write this for strain in y direction, so 1 by E is common, however, so sigma y will be the dominating force, the other two forces are not considering here, and other two forces can be written as sigma, that is z minus mu times sigma x, which means strain in y direction, strain in y direction. So similar way, strain in z direction if I write, so it is sigma z minus mu times sigma x minus mu times sigma y. So it is strain in z direction, strain in z direction. So now I got all the three directions x, y, and z. So if I write it for total volumetric strain, that is EB, which is equal to, so that is sigma x plus sigma y sigma z divided by E minus 2 times, because in all the three terms we have 2 mu's. This is 1 and these 2. So in all the three terms we have 2 Poisson's ratios, right? So for this, if I take it common, sigma x plus sigma y plus sigma z by E, and which I remained with 1 minus 2 mu times sigma x plus sigma y plus sigma z. So if I multiply this term and rewrite this equation, I will get for strain x, strain y and strain z, right? So now I will simply rewrite this equation to simplify this. 1 by E times sigma x plus y plus z multiplying 1 minus 2 mu. So taken this part outside. So this is the total volumetric strain when 3 mutually perpendicular forces are acting. First it is been considered in x direction, and second it is been considered in y direction, and later in z direction, and combining all three together, and total volumetric strain comes out to be 1 by E times sigma x plus sigma y plus sigma z times 1 minus 2 mu. Thank you.